Alright, what's up guys? This is Jahangir from MedPorium, and today we're going to be talking about Ohm's law. Now, Ohm's law is actually very simple in terms of the equation, and it's just voltage equals current times resistance. So over here, V is going to be voltage, and it will be denoted in our SI units of volts, or you're just going to see into something like V. I is going to represent our current, and our current is going to be in amps, or we'll just use A. And resistance over here is going to be denoted in ohms, or this sort of symbol. I think that's sort of a Greek letter, some sort of Greek letter, but me being me, I just forgot which one. So this is what Ohm's law pretty much is. It's voltage equals current times resistance. Now, what is the relationship between voltage and current, as well as current and resistance? Well, over here, as you can see, voltage and current are in a direct proportional relationship, which means if we increase the amount of voltage we have in our circuit, well, we're going to increase the amount of current that we have, and vice versa. Now, with current and resistance, it's sort of a different story, because if you wanted to isolate any one of these, like let's say we wanted to isolate resistance, we'd have to divide current over, so this is the type of relationship we'd get. Now, over here, this was just assuming that our resistance was constant. And now, over here in this equation, we're assuming that since if voltage is constant, if we have an increase in resistance, so if resistance increases, then current is going to decrease. I mean, this makes sense in a, I guess you could say, logical sense, because resistance is the opposition of the flow of electrons, and our current is described as the flow of electrons. So if we have more resistance, if we have more resistors or anything like that, we're going to decrease the amount of electrons that go through our circuit. So this is the sort of relationship that you want to be able to know, and I'll just keep our Ohm's law equation right over here, so then we can start looking at some circuits. So let's say we're looking at this series circuit over here. Now our voltage over here is 10 and our resistance is 5. So we only have one resistor, so all we have to do is just use Ohm's law to find our amount of current that is going through our circuit. So we're wanting to find I. So all we have to do is use Ohm's law, voltage equals current times resistance. The voltage that we have is 10, so that'll be 10 volts equals, and then we have the resistance. We're looking for the current, so I'll just do 5 ohms and then brackets I, and 10 divided by 5 is going to get us 2 amps equals our current. So over here, our current is 2 amps. All right, so what if we have something like this, where we have two resistors? So we have multiple resistors in our series circuit. So we're still going to be using Ohm's law, but we need to find the total amount of resistance to find the current that is going through this entire circuit. So total resistance, and this is a series circuit, so total resistance is going to be additive. So it's just going to be, if we label this like R1, R2, we're just going to be adding both of those, and that gets us our total resistance. So in this case, we have 5 plus 4, which is going to equal 9. And that is our total resistance for this circuit. Now, knowing that, now let's find the total current that is flowing through this entire circuit. Now, total current flowing through the entire circuit is going to be 27, that is our voltage, equals 9, and then that is our current. 9 is our resistance over here. So it's just 27 divided by 9. When you divide those over, our current is going to equal 3 amps. So 3 amps is flowing through this entire circuit. So now we could ask the question, well, how much voltage is being consumed in resistor 1, and how much voltage is being consumed in resistor 2? Well, all we really have to do is use Ohm's law and find that voltage of that specific resistor. So we're given our total current. So the amount of current that is flowing through this entire circuit is going to be the same. So 3 amps is going to go to this 5 ohms resistor, and 3 amps is going to go to this 4 ohm resistor. So all we have to do is find the voltage at resistor 1, which is going to equal our current. I'll just do total current times the resistors. So over here, this is just going to be 5 times 3, which gets us 15 volts. So 15 volts is flowing through resistor 1. Now what about resistor 2? Same exact thing, same exact process, but we're going to be using resistor 2. So this is going to be 3 times 4, which equals 12 volts. Now, I want you guys to notice something interesting. So let me just label these 15 volts, 12 volts. Now, as you can see, the total amount of voltage that we put into this entire circuit was 27. And guess what? The total amount of voltage that was consumed is 27 volts. So one thing you will know is that the amount of voltage put in will equal the amount of voltage consumed by the total resistance, the total, like each of these, since 15 plus 12 equals 27. 27 volts are being consumed, which is known as the voltage drop, and that is equal to the amount of voltage that we put in. So hopefully that makes sense to you guys. And this is actually what Kirchoff's law is. So I'm just going to be erasing some of this work over here. Kirchoff's law basically states that the total amount of voltage going through this entire circuit is going to equal 0. And this applies to other circuits as well. But knowing this, and we just pretty much showed that, we just proved our work showing that the amount of voltage that we put in was consumed by the resistors. So the total amount of the sum of voltage equals 0. Alright, so what if we have our resistors in parallel? Well, how are we going to find our total amount of current? Now, this is a little bit different from our series circuit, where in our series circuit, the amount of current that was flowing through each of those resistors was the same. Now, in our parallel circuit, it's going to be a little bit different. The amount of the amount of current that is flowing through each of our resistors is going to be a little bit different. And here's how we're going to show that. So, over here, when we're trying to find our total current, we need to find the current flowing through each of these resistors. So, we're going to be pretty much solving them using Ohm's law and treating them separately. So this will be R1, R2, and R3. So let's start with R1 over here. So we know Ohm's law, voltage equals current times resistance. So over here, all we need to do is know the voltage, which is 36. I'm not going to be writing the units for this one, just to make it a little bit more simple. And this is going to be 3. We have our current over here. So our current in this case for this resistor is going to equal 12 amps. So we'll just say we'll have 12 amps over here. Now, same exact thing, we're using Ohm's law over here. So this is going to be applied to resistor 2. So this is 36 equals, and we'll have 6, looking for our current over here. So 36 divided by 6 will get us 6 amps, which is going to be our current going through here. And over here in our resistor 3, we're going to have same thing using Ohm's law. So this is going to be I3R3, and this is going to be 36 equals 9. We're looking for the current. So over here, our current is going to equal 4 amps. So we have 4 amps over here. Now, we know the amount of current that is flowing through each of these resistors. And as you'll notice, the amount of current that is flowing through these resistors, as the amount of resistance increases, this is actually decreasing. So when we're talking about in our Ohm's law, we were saying that the relationship between current and resistance is inversely proportional, meaning, as you can see, the amount of current that is increasing, our resistance is decreasing. Or just for this example, it might be easier to see the fact that as we're increasing resistance, we are decreasing the amount of current that is flowing through these resistors. So now that we know that, let us find the total amount of current that is flowing through this entire circuit. But first, we need to talk about Kirchoff's current law, which states that the amount of current going inside our circuit is going to equal the amount coming out. And this also applies to our series circuits as well. But just knowing this, we know and we can derive the fact that our total amount of current is going to equal just adding all of these currents together. So this is 12 amps plus 6 amps plus 4 amps. which will get us 22 amps of total current flowing through our circuit. So what does this mean? Well, our current is going to be flowing from left to right, from positive to negative. Forgot to label these guys over here, but we're going to have 22 amps of current flowing this direction. Now we have 22 amps flowing, and over here, this is where 12 amps of current is going to be moving to resistance 1. So let me move these as well to create a little bit more space. So if 12 amps of current is flowing to resistor 1, then 22 divided by 12, we're going to be having 10 amps of current flowing this way. And over here, since 6 amps of current flow to R2, then we have 4 amps of current flowing. And those 4 amps of current are going to flow to resistor 3, and we're going to come back all the way down. Now, let me also create some space over here, and this current is going to be coming back, and we're going to have 4 amps of current coming down again. Then we'll have 6 amps of current coming down over here, so we'll have 10 amps of current, 10 amps moving all the way over here, and then we'll have 12 amps moving all the way back till we get 22 amps. So this is showing Kirchoff's current law pretty much, where the amount of current that we started with, that we're putting in, is 22 amps. And as we're moving down through our parallel circuit, our resistors are taking some current, going all the way down, but at the end, the total amount of current goes back and continues on. So the total amount of current that we put in equals the total amount of current that has come out from our circuit. Now, I want to show you guys something that's actually pretty interesting when you're looking at these parallel circuits. So if we wanted to find the amount of voltage that was flowing through each of these resistors, well, obviously we'd use Ohm's law for this case, and we're just treating these separately. So over here, the amount of current flowing through resistor 1 is 12. The amount of resistance is 3 ohms, and look at that. We get 36 volts flowing through this resistor. That's interesting. Does that happen to our other resistors? Well, if we apply our Ohm's law, we have current over here for resistor 2 is 6 times 6. Oh, well, will you look at that? It's 36 volts. Let's see for resistor 2. Well, 9 times 4, oh my gosh, that is 36 volts. And as you will notice, the only way we can have our resistance going up, which is affecting our current, is if voltage is constant. So you will notice with our parallel circuits, voltage will stay constant. This is the only way we can actually, use Ohm's law, is if in our parallel circuit is if our voltage is constant, which, as you can see, we're in this problem, we're just pretty much assuming that it is. So the amount of voltage flowing through our resistors is constant, which allows for us to look at this sort of equation over here, where increasing the amount of resistance will decrease the current only if our voltage stays constant. And when we're looking at our series circuits, so I'll scroll up a little bit over here. When we're looking at our series circuits, we were also noticing that since current is the same, the amount of voltage increases as we increase the amount of resistance. So over here, we had total amount of voltage was 27, and we have a resistor 5. 5 is greater than 4. So more voltage is going to be flowing to the higher resistor. So over here, as you can see with our series circuit and our parallel circuit, we need one of these variables to stay constant in order for us to devise that sort of relationship. So I just thought that was something pretty interesting, looking at Kirchoff's current law, looking at Kirchoff's voltage law, knowing that one of them has to be constant in order for us to devise a relationship. Alright, so for our final problem, what if we have these resistors in parallel and in series in the same circuit? So what we're going to have to do is treat these parallel resistors as if they were in a series. Now to do that, we need to find the total resistance that's between these two, so then we could just turn it into acting like a series resistor. So how do we do that? Well, that is when we're going to use our equation 1 over resistance total equals 1 over R1 plus 1 over R2, and etc. if there are more. But since we only have two resistors that are parallel right over here, we're going to be using this equation. Now this equation is specifically for if we have a parallel circuit, we're trying to find the total resistance. So And another way just of modeling this is you could just do 1 over R1 plus 1 over R2, and then to the -1 power, since that's what the resistance total is going to look like. So over here we have 1 over 10 plus 1/2. So this is 1 over 10 plus 1/2. And if we just pull out our calculator over here, 1 over 10 is 0.1 and 1/2 is 0.5. So 0.1 plus 0.5 and then to the negative power, and we're going to get 1.7 ohms as, oh, that was a terrible ohm right there, ohms. So this is going to be 1.7 ohms in between this guy over here. So what that basically looks like is somewhere over here, we're trying to turn these two into a series where we have a series resistor that is 1.7 ohms. Now, let's move on to our 6 ohms. Well, it's in a series already. We don't really have to do much to this guy. So over here, now we have to convert this into a series resistor. So pretty much the same process, but now we have 1 over 20 plus 1 over 5. So if I bring out the calculator over here, we have 1 over 20 plus 1 over 5, -1 power, and that gets us 4 ohms. So over here, we're just kind of visualizing the fact that this is in a series and this is going to be 4 ohms. So now we found the resistance of this guy over here, turn those into series resistors. So all we really have to do now, since this is a series, these resistors are in a series, we can just add them up. So the total resistance is going to be 4 plus 1.7 plus 6, and that is going to get us 11.7 as our resistance. So this over here, 11.7 ohms, is our total resistance. So now we need to find the amount of current that we have. So I'm just going to delete, actually I'll leave the equation over here, just if you guys want some notes, but I'm going to delete some of this stuff over here, So now we need to find the amount of current that is flowing through this entire circuit. Now, since we are in a series circuit, the amount of current that is flowing is going to stay constant. So then we can just pull out our Ohm's law, and we know our voltage, 24 volts, or I'll leave it as whole numbers just to make it a little bit easier. And then resistance, we have 11.7, and we're trying to find our current. So this is just going to be 24 divided by 11.7, and our current is going to equal 2.05, about 2.05 amps. So 2.05 amps is going to be flowing through our entire series current. Now, let's actually try to find the voltage for each of these resistors and see if that adds up to our total voltage to, check our answer and see if all the math that we did was correct. So I'm going to be deleting some of this stuff over here. Delete that and delete this over here as well. All right, so we need to find the amount of voltage that is going through each of these resistors. So over here, we treat this as 1.7 ohms as this resistor over here. So we're just going to use Ohm's rule. So I'm just going to label this as, this is going to be our R1, R2, R3, just so we can keep track of everything. So like we said, the amount of current flowing through this entire series is going to be constant. The voltage going through each of these is going to be a little bit different. So let's use Ohm's law. So we need voltage of our first guy, current times resistance. So we know our current, we know our resistance. This is 2.05, and then times 1.7, and that is going to get us 3.485 volts. All right, so that's going to be the voltage for our resistance over here, the first guy over here. So now let's go this guy over here. So we're going to use Ohm's rule again, Ohm's law again. So over here, our voltage, and let me label these as 2. So our voltage is what we're trying to find. So we have current. Actually, what I could have done is just leave this as current total, just so we don't confuse anyone, because like we said, the amount of current flowing through this entire circuit is going to be constant since we are in a series circuit. So over here, our resistance is going to be 6 times 2.05. That's going to get us, actually let me move some of this stuff over here just to make it a little bit easier for you guys. So I think I put resistance first before current, so I'll just make it a little bit easier. 2.05 times 6, and that will get us, let's see, 12.3 volts for this guy over here, and last one over here. So we need to find our voltage, so I total over R3. Pretty much the same process. We know our current, 2.05, and then that's going to be multiplied by 4 ohms, and 2.05 times 4 gets us 8.2. So now let us add this guy, and this guy, the total voltage drop, and if it equals 24 volts, then we did our math correctly. So this is going to be 3.485 plus 8.2 plus 12.3. Now let's see what that is. Plus 8.2 plus 12.3. And indeed, we get 23.98, but I mean, you just round up, it'll be 24 volts. So that is how we can check that our math is correct, because with a series circuit, we need to understand that the voltage drops are going to equal the amount of voltage that we put in. And the sum of those voltages, voltage going in subtracted by a voltage drop, that is going to equal 0, because that was our Kirchoff's voltage law that we talked about before. All right, so let's say we wanted to find the specific amount of current that is flowing through each of these resistors. Well, first we want to label each of these resistors. So this is R1, R2, this guy over here, R3, but we don't really have to worry about this guy since it's already in a series. We know 2.05 amps is flowing through this guy. So this is R4, and this is R5. So if we remember, when we were calculating our voltages, we remember that this guy over here was 8.2 volts, and this guy over here was, I believe, 3.485 volts. So to find the amount of current that is flowing through each of these resistors, we know the amount of voltage that is flowing, the total amount of voltage. So all we have to do is bring up Ohm's law, and we know that the voltage flowing through each of these guys is going to be 3.485. Remember, in a parallel series, when these resistors are in parallel, our voltage is going to be constant going through each of these. So this is going to equal, we're trying to find our current, and we know our resistance is 10. To make this a little bit easier, I'll just rearrange these to 10 over here. So this is going to be 3.4887 divided by 10, which gets us, our current is being 0.3485 amps. Now, let me label this guy over here as a 1. So over here, let's try this guy over here, resistor 2. So this is going to be finding our current. So we know the voltage that we have for this circuit is 3.485 volts, and this is, just to make it a little bit easier, I'll just do 2I, and this is 3.485 divided by 2. This gets us 1.74, and I'll just leave the rounding over here, just round down. So this is 1.7 volts. Now, if we wanted to add both of these up, we would get 2.08 amps. So the reason why we got a little bit of higher amps is because we were rounding our numbers. But as you can see, that is pretty much, it's very close to 2.05 amps. If we had, perfect numbers, then we would get to 2.05, but since we are rounding all the way down here, we got 2.08. But as you can see, the amount of current that went through this entire circuit was 2.05. But for this resistor over here with a 10 resistance, the higher resistor had the least amount of current flowing, while the lower resistor over here, the lowest resistance, had the most amount of current flowing. So that makes sense, because when we're looking at our Ohm's law, we derive the fact that if we have a higher amount of if we have a higher amount of resistance, we have less current. If we have less resistance, we have more current, since they are inversely proportional. So over here, I want you guys to find the amount of current going through each of these resistors, R4 and R5, and see if you can find that. All right, so let's start with resistor 4 over here. So our voltage is going to be V, here let me do voltage equals I for R4. So we know our voltage is 8.2, so this is going to be 8.2, and then that is 20 I, so 8.2 divided by 20, 8.2 divided by 20, we get current equaling 0.41 amps. And over here for our R5, we have 8.2 volts equals, and this is going to be 5. So this is 8.2 divided by 5, and this is 1.64 amps, and 1.64 plus 0.41 gets us 2.05 amps. So the rule still follows, that relationship still follows, where if we have more resistance, less current flows. If we have less resistance, more current flows. Alright, and that concludes our video over Ohm's law, resistors in series, parallel. Hopefully this made sense to you guys, because at first it is a little bit intimidating, but once you get through the math, it gets pretty easy. And as always, a Pomodoro a day will make you a doctor someday. I'll see you guys in the next one.